Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Sahib Noor and welcome to a new lecture of Electromagnetic Field Theory. This is our lecture number 10 of the course and we will study numerical problems related to chapter number 2. The title name of the chapter is Vector Analysis. So our main topics of this lecture, we have to discuss the numerical problem related to the del operator, which is a three-dimensional vector operator. So when it's operate on a scalar, we will call it the gradient of a scalar field. And then we have to discuss the divergence and a curl of a vector field. And in the last part of this lecture, we have to discuss some integral calculus. It may be a surface integral or a line integral as well. So in this slide we will discuss the gradient of a scalar function. Some scalar function will be given and we will find their gradient. So here scalar function is r square and we have to prove that del of r square is equal to 2r vector. And then in second part we will have to prove that gradient of 1 over r is equal to minus r cap divided by r square. And in third part of this question we will develop a general formula for the gradient of any power of r. And let's start that our vector position vector is in the Cartesian coordinate is equal to r vector is equal to x minus x naught I plus y minus y naught j plus z minus z naught k. And the magnitude of this position vector in the Cartesian coordinate, we have to just take a square of the component of I, j and k, and we will have x minus x naught square plus y minus y naught square plus z minus z naught square. Now we will operate del on the r square and we will have del by del x of r square into I plus del by del y into r square j plus del by del z of r square into z k. And after derivative with respect to x, y and z, we will have 2 x minus x naught I plus 2 y minus y naught j plus 2 z minus z naught k. And remember that this is 2 times of the position vector, and the position vector is split into a magnitude and its direction. So we have proved that the gradient of r square is equal to 2r vector r 2 into magnitude of r into r k. In the part B, we have to prove the gradient of 1 over r is equal to minus r cap divided by r square. So we have just write 1 divided by r represent the magnitude of the position vector, and for r we will write under the root x minus x naught square plus y minus y naught square plus z minus z naught square. Here r square is equal to x minus x naught whole square plus y minus y naught whole square plus z minus z naught whole square. And if you have to find only r, you will have to take square root on both sides. So r will equal to this. And then we will partially integrate this 1 over r with respect to x, with respect to y and with respect to z. We will just put these expressions in the above expression. So the value of this is equal to this, and the value of del over del y into 1 over r, this is the value of del over del y into 1 over r, and this is the value of del over del z into 1 over r. So we will put these values in this expression and we will obtain x minus x naught I plus y minus y naught j plus z minus z naught k divided by this term. And remember that as we have write r whenever the power is 1 by 2. So here the power is 3 by 2. So the denominator term is r cube, and the above term is the vector form of the r, which is known as the position vector. So we just write r vector and then use the definition of vector, which is magnitude into its direction. So r into r cap, r will cancel with the r cube, and we will have r square in the denominator term. So the del of 1 over r is equal to minus r cap divided by r square. And from these two expressions, here the power of r is minus 1. If you take the r term in the denominator, so you will have del of r inverse r. The power of r is minus 1. So if power is minus 1, so you can write it minus, this is the power, this n represents the power. So if the power is minus 1, the minus will appear here, and then we will lower the power. So we will lower the power. If power is minus 1, so it will minus 1 in the denominator. So you will have plus 2, and then you will have to write the unit vector. This is the formula for any. And here we have the power of r is 2, so power will be lower. So we have here 2, and we will lower the power. 2 minus 1, which is 1, r1. So 2 into r power 1, and then we will have a unit vector. In next slide, we have to calculate the gradient of some scalar function as well. But now we have three different expressions which are the function of x, y, z, and we have to calculate the gradient of each of the given function. So first we will operate del on f, and we will use the differential operator in the Cartesian coordinate, because the expressions are given in the Cartesian coordinate. So we will partially differentiate these functions with respect to x, y, and z. So when this is differentiated with respect to x, we will have 2x with the unit vector. Similarly, this part will be differentiated with respect to y, so we will have 3y square into y cap, and the third part will differentiate with respect to z. We will have 4z cube and z unit vector, and you can differentiate the remaining expression as well. So in the third part, we will differentiate these functions with respect to x, y, z. Remember that the differentiation of exponential term is with respect to some specific coordinate will unchanged. So if we differentiate ex with respect to x, we will have ex, and then sine y and take log of z. These are the constant function with respect to x, and we will put x cap plus the derivative of sine with respect to y is cos, so we will have a cos y, and the x and z term are constants with respect to y. And in the third derivative, we will differentiate this expression with respect to z, so only log z will be differentiated, and the derivative of log z is 1 over z. So we have 1 over z, and the x and y term are kept constant. So let's start our last problem related to the gradient of a scalar function. A function v which depend upon x, y, and z, and we have to find the magnitude and direction of the maximum rate of increase of v at a point 1, 2, and 3. So, and in the second part, we have to calculate the rate of increase of v at p in the direction of the origin. So first we have to calculate the gradient of v, and we will operate del on v, and we will differentiate each term of v with respect to x, with respect to y, and with respect to z. After differentiation, you will see that e power minus z is the common term, and then we will have to derive the maximum rate of increase of v at the point 1, 2, 3. So for x we will put 1, for y we will put 2, and for z we will put 3. So if you see that when we put the value of x over here, so we will have cos pi by 2, and cos pi by 2 is equal to 0. So the x term will vanish and we will have only y and z component. And in second part they ask that find the rate of increase of v at p in the direction of origin. So we have to obtain first a vector and then its unit vector, and then we will multiply the unit vector with the gradient of v. So we have to obtain PO, which represents the position vector in the direction of O. So we will subtract these points from the points of x, y, z at the origin. So 0 minus 1 into ax plus 0 minus 2 into ay plus 0 minus 3 into az. So we will have minus ax minus 2ay minus 3az. And the unit vector of this vector is minus 1 divided by under root 14 into ax plus 2ay plus 3az. And now we will multiply this unit vector with the gradient of v at p, and we will obtain our result for the second part, which is the rate of increase of v in the direction of the origin, which is 0.0485. Now let's solve some problem on the divergence of a vector field, and we will operate L on some vector function in the dot operation. So we have to find the divergence of D, if D is a vector function, and you will clearly see that here are the unit vector at the expression of D. So ax and ay and az are the base unit vector in the Cartesian coordinate. So when we have to find the divergence of D, we will just write the divergence of D in the Cartesian coordinate as del or del x dx plus del or del y dy plus del or del z dz. So here we have to put the x component of D, here we have to put only the y component of D, and here we have to put only the z component of D. After partial derivative of D, we will have minus e power minus x sin y plus e power minus x sin y plus 2, and this part will cancel with this part and we will have only 2. So the divergence of D is 2. And in the following parts we have to also calculate the divergence of VA, the divergence of VB, and the divergence of VC, and these functions are given in the Cartesian coordinate. So our formula will be the same. So here if we find the divergence of VA, so this will be the divergence of VA, and we will put, instead of dx, we will put VAX. So this is the x component of a VA function, and here we have to put the y component of a VA function, and here the z component of a VA function. And similarly we will do the following, and our answer will be 0 y plus 2x plus 3x, and for divergence of VC our answer will be 2 into x plus y. So these are the divergence of some vector function in the Cartesian coordinates. In this slide we will discuss the divergence of magnetic flux density, and in statement they say that the magnetic flux density B outside a very long current carrying wire is circumferential, and it is inversely related to the distance to the axis of the wire. So B can be written as B is equal to A phi, as they say that this is circumferential, so the angle will vary and we have to take only the phi unit vector, and they say that it is inversely proportional to r, so we have to insert a constant, so k is constant. So we have to find the divergence of b in the cylindrical coordinates, because y symmetry is related with the cylindrical coordinates, and the cylindrical coordinates are r, phi, z, and the divergence of a function in cylindrical coordinates can be written as 1 over r del r dr. So this is the radial component of the given function, plus 1 over r del phi of d phi, which is the phi component which is given to us, and plus del z dz. So here in our expression we have only phi term of function b, so we will write here k over r and will differentiate. So b phi is equal to k or r, dr, and bz is equal to 0. So when we find the partial derivative of b of phi with respect to phi, we will have 0, because here we have the radial function 1 k divided by r, and we are going to differentiate it with respect to phi. So the divergence of b will be equal to 0. And next problem, we have to find the divergence of a function v, which are given in the spherical coordinates. So we have the three components: the r component, the theta component, and the phi component. So we have to find the divergence of a vector v in the spherical coordinates. So the divergence of any vector in the spherical coordinate is given by 1 divided by r square del r square, and the rth component of a vector, plus 1 divided by r sin theta del theta a theta. This means that the theta component of a function, and it will multiply with the sin theta, plus 1 divided by r sin theta and del phi, the phi component of a vector. So when we put v instead of a, our expression will be 1 over r square del r into r square. This is the r square of the formula, and r cos theta, this is the r component of a vector v. So this r square and this r will multiply, and we will have r cube, and we will differentiate it with respect to r. So we will have 3r square into cos theta, and then the remaining part. So after differentiating with respect to theta and phi, and after some calculation, our answer will be 5 cos theta minus sin phi. Now in this slide we will find the divergence and curl of a same function. So in part A we will find the divergence, and then in part B we will find the curl of a function. So first we have to look that our function is given in the r, phi, and z. So we will use the cylindrical coordinate. So the divergence of any vector in the cylindrical coordinate can be written as 1 over r del r dr, plus 1 over r del phi of b phi, plus del z of bz. So here we have to put the r component of a vector, the phi component of a vector, and the z component of a vector. So after putting the value of vr, v phi, and vz, and differentiate with respect to r, with respect to phi, and with respect to z respectively, we will have 2r into 2 plus sin square phi, and the phi differentiation of v phi with respect to phi, we will obtain r 1 minus 2 into sin square phi, and the differentiation of vz with respect to z is equal to 3. Now after putting the value of del r rvr, del phi v phi, and del z vz over here, and after the calculation we will have 8, which is the divergence of the function v. And in the second part we have to calculate the curl of a vector v, and in the cylindrical coordinate the curl of any function a is given as 1/r, and then we have a 3×3 determinant. In the first row we have to write the component of the base unit vector in the cylindrical coordinate along with the metric coefficient, and the second row we will write the differential operator of the cylindrical coordinate, and in the third row we have to write the component of vector a along with the metric coefficient. So now we can write the component of vector a, which are r into 2 plus sine square phi, and the phi component of vector a is sine phi cos phi, and this r is the metric coefficient. And then we will write the z component of a vector v, and after calculating the determinant and will multiply it with 1/r, so our determinant will be equal to 0, and then it will multiply with 1/r, so the overall result is 0. So the curl of v is 0 while the divergence of v is 8. Now in this slide we will discuss a line integral in which a function v is given, and we have to find the line integral of this function from point A to point B along two paths, path 1 and path 2, and the points are, point A is 1, 1, 0, point B is 2, 2, 0, and in figure you can see that these points lie in xy plane. So at point A the value of x is 1, the value of y is 1, and z is 0, and at point B the value of x is 2, the value of y is 2, and z is equal to 0. So we need a differential length in the xyz coordinates or in the Cartesian coordinates. So the differential length is dl, which is equal to dx x cap plus dy y cap plus dz z cap. And if we choose path 1, which can be further divided into two paths, one is the horizontal path and the next one is the vertical path. So the horizontal segment, the dy and dz will equal to 0. So for this part the y and z will equal to 0, and our differential length will be only the x element. So dl will equal to dx x cap, and for this horizontal segment y is fixed, which is equal to 1. So from A to here the value of y will not change and it will equal to 1, and the dot product of v dot dl will give us y square dx. And if we put the value of y is equal to 1, so we will have only dx. So the value of v dot dl for this line is equal to dx, and we will integrate this from 1 to 2, and our answer will be equal to 1. And for the vertical length, for this vertical length, the dx and dz is equal to 0, and our differential length element will be only dy y cap. And for this vertical segment, our x is equal to 2, which is fixed, and v dot dl will equal to 4 into y plus 1 into dy, and we will integrate it again from 1 to 2, and our answer will be 10. So our distance is complete from A to B. Our two values, which is 1 for horizontal value for horizontal segment, and for the vertical segment we have 10. So from A to B the integral v dot dl is equal to 1 plus 10, which is equal to 11. In the second part we have to calculate the line integral from A to B in the direct path, which is the displacement. And for the displacement we know that the value of x and y vary similarly, so x is equal to y and dx will equal to dx, and as we have calculating the line integral in xy plane, so dz will equal to 0. So our differential length will be equal to dx x cap plus dy y cap, but for y we will put x as y and x are equal. So here dy is equal to dx. But remember that the unit vector will not change, and when we take the dot product of this differential length with v, our remaining term will be equal to 3 into x square plus 2 into x dx, and we will integrate this from 1 to 2, and our answer will be equal to 10. So for now we compare these two integrals, or we comparing these two answer along different paths. So path 1 will give us 11, and path 2, which is the direct path, and along path 2 the line integral have answer equals to 10. So these two paths have a different answer, so we can say that the given function v is the non-conservative function. Now at the last problem of this lecture, we have to verify the Stokes theorem for a given function which is given in the Cartesian coordinate. But our symmetry will be triangular and is shown in the figure. As we know that the Stokes theorem relates a surface integral of a curl of an open surface into a line integral of the same function or a closed loop, and we have to calculate the curl of the given function first. So the curl in the Cartesian coordinates, we will obtain that the curl of the given function is equal to minus 2y I cap minus 3z into j cap minus x into k cap. And now you will have to choose a surface, and for the given figure the surface is lie in the yz plane, so the surface must be parallel to the x-axis, and the differential surface will be equal to dy dz. So this is made by y and z component, and it is parallel to the x-axis. Now we will take the dot product of this surface element with the curl of vector v, and we will have minus 2y dy dz. And now we will integrate this function from 0 to 2. This is the value of y, and z varies from 0 to 2 minus y, as we can obtain this relation from here, in which if y is reducing, z will increase up to 2. So the value of z plus y over this line is equal to 2, and we can easily obtain the value of z, which is 2 minus y. So we will integrate this function with respect to z and with respect to y. The value of y will vary from 0 to 2, while the value of z is vary to 0 to 2 minus y. So first we will integrate it with respect to z, and then we will put the limits of z, and finally we will integrate it with respect to y, and our answer will be equal to minus 8 divided by 3. Now we have done the left hand side of the Stokes theorem. For the right hand side of the Stokes theorem, we have to split the closed loop. If we start from here, from 0 to 2, and then from 2 to 2, which is the value of z, and then to the origin. So this is our closed loop, and we have to solve the line integral into 3 segments. In first segment, we will take the dot product of function v with the length element, but here the length element is equal to dyj. So we are moving from origin to a point where the value of y is only varying, the x and the z component are kept fixed, which is 0. So only the length element contain only divide term. So when it apply with the v in dot product, so we will have 2y z dy, as z is equal to 0. So if you put z is equal to 0, so our whole function will be equal to the v dot dl for the horizontal segment is equal to 0. Now for the inclined segment where y and z are varying, so when y increase, z will decrease, so we will put a negative sign, so dy j minus dzk. So as y and z are varying in similar manner, so when y decrease, z will increase, or when z increase, y will decrease. So we will put a negative sign, but the direction will be kept the same. So dyj minus dzk, but here z and y are equal in magnitude, opposite direction, so we put dy instead of dz with negative sign. Now we will take dot product of this length element with the v, and we will have dy 2y z dy minus 3z x dy is equal to 2y z dy, as the x value of x along the inclined plane, the plane lies in yz plane, so x is equal to 0, so this part will equal to 0, and we will have only 2yz dy. And now we will integrate this, and along the segment, along the inclined segment, the value of z is equal to 2 minus y. So we can also put the value of z here, and we will have 2y into 2 minus y dy. And after multiplication, the v dot dl will equals to 4y minus 2y square into dy, and we will integrate this from 2 to 0, because we start from the lower part of the inclined plane to the upper part. So at the lower part, the value of y is equal to 2, at the upper part, the value of y is equal to 0. After integration, we will have minus 8 by 3. Now we will have the vertical part. We will have to find the line integral for the vertical part from 2 to 0, where the value of z is 2, and here we have all components x, y, z is equal to 0. So the remaining part, in which we have to calculate the line integral for the vertical segment, in which we have to move from 0, 0, 2 to 0, 0, 0. So here only z component are varying, so our length element will contain only z, but here the direction is opposite to the positive z axis, and we will put a negative sign. And after dot product of dl with v, we will have minus 3z x dz. We will put x is equal to 0, and our v dot dl will equal to 0. So no need to find the integral of this segment. Now we are summing the loops of v dot dl. Our first segment has 0 answer. Our second segment, which is the inclined segment, has value minus 8 by 3, and the vertical segment is also equal to 0. So the loop of the line integral will have minus 8 by 3, which is the right hand side of the left hand side, and the right hand side has the same value. So we can say that the Stokes theorem is verified for the given function. So let's sum up our lecture number 10. We have studied some numerical problems related to gradient of a scalar function, and we have solved the gradient of scalar function in 3 different coordinates. And then we have studied the divergence and curl of a vector field in different coordinates, and at the final part we have discussed a line integral and a surface integral, which appear in the Stokes theorem. In next lecture we will study electric charge at rest, and the study of electric charge at rest is known as electrostatic, and a well-known law which is related with the electrostatic, and this law is applicable for a point charge at rest, and this is called the Coulomb law, and we will discuss the Coulomb law for the free space and for the material medium as well. If you have any difficulties related to this lecture, you can contact me at my email. Till then, Allah Hafiz.